Hello everyone, welcome to our differential equation class. In this video we are going to focus on finding the phase portraits of solutions to 2x2 system of linear differential equations in the case that the coefficient matrix has either complex eigenvalues or real and different eigenvalues. So, yep, that's the plan for today. Okay, let's start our video where we left in the previous video. And in the previous video, essentially, we reviewed the solution formulas for the solution of a system of linear equations like this one, where A is a constant matrix with real eigenvalues 2x2. We said, suppose we name the eigenvectors and eigenvalues lambda plus v plus and lambda minus v minus, and let's assume we were considering only this case, that the eigenvalues are complex valued and so are the corresponding eigenvectors. So we have fundamental solutions like this, and then any other solution is linear combination of these two. And if we want to know the graph of any solution, what we need to understand is the graph of these fundamental solutions. And we concentrate in the last video on the first solution, fundamental solution here, and we graph that solution on the phase space. And the graph depends on which direction these vectors are pointing. So we choose some arbitrary directions, this direction and that direction, and depend on the coefficient alpha. Whether the coefficient is positive, negative, or zero, the graph is very different in those cases. And we study first the case alpha positive, and we found that the solution is actually a spiral that is spiraling from the origin outside to infinity, as this is the direction, this arrow is the direction as time grows. We are moving from the center to outside. And this is in the case alpha positive. The way we found this graph is very simple. We first draw the vectors a, b and their negatives, these four vectors, then the ellipse that is formed by these vectors, and then we gave a couple of values to the solution. We evaluate the solution at 0, and when we evaluate the solution at 0, everything disappears and we get only a. So the solution at 0 crosses the ellipse at the vector a. And then we compute the solution at the different time positive, such that the cosine is 0 and the sine is 1. And then we ended up here, which is a vector, the solution at that point is proportional to the vector negative b. So this point moves toward this point. When alpha is positive, this factor is bigger than 1. So we are in a vector, the solution vector is a vector longer than the vector negative b. So I put it here just to do the picture. So the solution has to go from here to here. The solution has to rotate because of this part of the solution, has to get larger and larger in magnitude because of that factor. So the solution has to be an ellipse like that. This part inside the ellipse is for t negative when this factor is less than 1. The part outside the ellipse is for t positive when this factor is bigger than 1. And then we cross the ellipse at t equals 0 when this factor is actually 1. And this is how the picture looks like. We repeated the same procedure for alpha negative, and we found that the solution is still an ellipse, is still a spiral, sorry, but instead of spiraling towards infinity and getting bigger and bigger as time grows, for alpha negative, the solution comes from t negative, from outside the ellipse, crosses the ellipse at t equals 0, and then goes inside the ellipse for t negative. It's just because the sign in the exponential is the opposite sign as before. So the ellipse, instead of going towards infinity, when alpha is negative, the ellipse goes towards 0. So we can see these pictures in an interactive graph that we have in our course webpage. So let's go there now. Here we are in the interactive graph in our class webpage. You go to interactive graphs, then GeoGebra graph, and the 2x2 complex eigenvalues option. And you're going to have this picture where this vector here is the vector that we call A, the real part of the eigenvalue V+. This is B, the imaginary part of the eigenvalue V+. And we have different vectors in our picture, so you can grab the endpoint here and move it somewhere. And the same here. So let's put this vector, which is closer to the vectors we have in our picture. So if you click here, you are going to have the negative of these two vectors. If you click here, you are going to have the ellipse. Recall this ellipse is important because this is, if you click here, you have the first fundamental solution, the one we did in our picture. But this is the case alpha, this is the real part of the eigenvalue lambda r, alpha equals 0. When alpha is 0, the solution moves on the ellipse. At t equals 0, we are at the vector A, like we found before. And then when t moves, the solution just spirals forever. So it moves on the spins forever. It moves on the ellipse. If we go to negative time and then we go from negative to positive times, the solution does the same forever. And let's go back to time t equals 0. There it is. So what happens when alpha is positive, which is the first picture we did? Well, we got a spiral, isn't it? So there it is, the spiral. The more positive alpha, the faster the spiral goes to infinity. So let's put the value like this. Okay. So now at t equals 0, we are still with the solution at the vector A. And then t positive, we move in the direction of negative b. Here is negative b, more or less. It's hard to pinpoint exactly negative b. But here we are at negative b. The solution is longer than negative b because alpha is positive. And then we keep going in time, and the solution still gets longer and longer. Well, it shortens a little bit in some parts, but in general, it's going to get longer and longer as t grows. Look at here. How long is the solution vector? The magnitude of this vector goes to infinity when t goes to infinity. And the direction, what is the direction of the solution? The solution spins forever, so there is no limit in the direction, spins forever, and the magnitude, look, is so big that it doesn't fit in our graph anymore. So this is what happens when, what happens in the opposite limit when t goes to negative infinity. Well, when t is negative, recall at t equals 0, the solution is crossing the ellipse. At t negative, the solution is inside the ellipse. And when t goes to negative infinity, the solution still spins, but the magnitude got smaller and smaller and smaller and goes to 0. If I had more values negatives, then the solution keeps spinning forever and getting shorter and shorter the vector. So when t grows, well, it does what we saw it does. Crosses at 0, go to infinity. Okay, that is the solution for alpha positive. What this solution is doing when alpha is negative. So let's go back to 0. There is 0, and this is negative. Now we are alpha negative. At t equals 0, we are crossing the ellipse, but now we are going inside the ellipse as t gets larger and larger, because when the solution is in the direction of negative b, the solution vector is shorter now, because the ellipse has the solution has an exponential with a negative exponent. And then when t goes to plus infinity, we go towards the origin. The solution vector, you see, spins forever, but it gets shorter and shorter, and the limit of the magnitude is 0. When t is negative, here we are outside the ellipse, but moving towards the inside always. So let's put it here. You see, we are very far away for t negative, but spinning towards the center. This is because alpha is negative. Let's put it back in 0. Alpha negative. Let's what happens if with these solutions, with any of these solutions, if we have different vectors a and b? Well, the solution gets deformed in the corresponding way, but the essential behavior is the same. There is one behavior that you see, the spinning of the solution is always from a to negative b, and because of the relative positions of vector a and vector negative b, the solution spins, in this case, clockwise. But if the solution would have a vector negative b in the other direction, then the solution still goes from a to negative b. Let's go to alpha positive to see a little bit more clear. Goes from a to negative b, but now negative b is in the opposite direction it was before, so now the rotation is counterclockwise. So clockwise or counterclockwise depends on the relative position of the vectors a and b. There. So if the relative position is like this, the vectors, then the solution goes clockwise. If the relative position is like that, then the solution goes counterclockwise. But always from a to negative b. So it's easier then to remember. A to negative b. So that is one thing we wanted to mention. The other thing is what happens with the second solution. The other fundamental solution, this is one of the solutions, the fundamental solution. What happened with the other? Well, it's right here in a different color, and let's take that away. It's very similar behavior to the first fundamental solutions. The only thing is we cross the ellipse at b here. In the first fundamental solution, we cross the ellipse at a, and here we cross it at b, and then the behavior is similar. The second fundamental solution is a little bit behind the first, but other than that, it does the same thing. So if you have the behavior of one fundamental solution, you have the behavior of both, because the second fundamental solution is just coming a little bit after the first. So that's that. And for alpha positive, for alpha negative, the same behavior, both go towards the origin, but one is always a little bit behind the other fundamental solution. And when alpha is 0, both spins in the ellipse, one behind the other, a little bit. And this is the general behavior of this fundamental solution for different values of the parameters. You can have one or the other. So let's put one. And so you can use this interactive graph to have an intuition how these solutions behave. Here we have a typical homework problem for this type of picture. So we don't give you the matrix, we just give you what are the eigenvalues and eigenvectors. We give you alpha. For example, in this case, it doesn't matter the numerical value. Alpha is positive in this case. Beta is not important. We have the vectors A and vectors B, and we need to plot on paper, like we did in the previous video, this solution, which is the fundamental solution that we call number 1. A, B. So you know how to do the graph. So this is the most important part of the exercise. Do on paper, on your own, the face portrait of this solution. Okay. And use to do this picture what are the values of the vectors A and B, and that alpha is positive. This is the important thing. So then you have in this picture, you have essentially the vectors A and B that correspond to this picture. You can actually draw the ellipse if you want. It's not okay. Let's see if I can. There it is, the ellipse. And in the problem, we give you 4 curves. This one, this one, this one, that one. They look all very similar, but actually they are all different. For example, Let's put these two together. You see they are not the same curve. What is the main difference? Well, let's see where we are at t equals 0. At t equals 0, let's move the time. Oh, at t equals 0, we are in the vector A. That's a good sign. And then it's moving towards the vector negative b. So for that is what happens in the, if you compare with your picture, that is what happens in the real solution. And then we are going outside. Okay, so this solution looks that satisfies all the properties we want. At t equals 0 is in the vector A, it moves toward the vectors negative b, and then it's moving outside. And you see here there are two vectors there. It's easier to see. This is the solution vector up to the point in the curve, and this solid vector here has always length 1, and this is a unit vector in the direction of the solution. This is a vector that helps you answer the questions in the problem. So it looks like curve 1 is actually the curve that for this problem, because it matches what we graph already. So what about the curve 2? Why is not curve 2? Well, let's go back to t equals 0. At t equals 0, we are in the vector A. That's good. But then you see this solution is moving towards the vector b, and the solution of the problem, we know it moves towards negative b. So 2 cannot be. So what about 3? Where are we with at t equals 0? Where is t equals 0? It's more or less here. Oh, at t equals 0, look, we are at the vector negative a. That's not what happens with the solution. So this cannot be the solution, because at t equals 0 we are in the vector negative a, and our solution is at vector a. So that cannot be. This one, at t equals 0, where are we? At t equals 0, we are also in the vector negative a, and then we are spinning. Well, it doesn't matter where we spin. At t equals 0 is in the ground position, the solution. So this cannot be. So it has to be solution 1. Perfect. So we go here and we say solution 1. Then use the graph below to determine the limit of the magnitude of the solution when t goes to plus infinity. Well, let's put t really big. What is the magnitude of the solution? The magnitude of the solution is the length of the solution vector. You see it's getting bigger and bigger because alpha is positive. The reason is alpha is positive. So then we go back here and we say, yeah, that goes to infinity for sure. What are these vectors here? These are unit vectors in the direction of A, unit vector in the direction of B, and this is the unit vector in the direction of the solution. This vector here, the vector u, is graphed. Is the solid vector here. This is the unit vector. What happens with that vector when we move time? Look at the solid vector. Spins, 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 spins forever. So does it have any limit when the time t goes to infinity? No, it's going to spin forever. We are in a spiral. So no limit here. What about the limit when t goes to negative infinity? Well, we are in the case recall alpha positive. So when t goes to negative infinity, so when we go to the past, what happens? We can see it in the picture, right here. Look, the solution goes towards the center. We are going to stop here at some point, but because we have a limit, we are not going to negative infinity, we are going to negative 18. But if we continue going to infinity, negative infinity, we are going to end up at 0. So the magnitude of the solution here, because alpha is positive, and then when t goes to negative infinity, that has to go to 0. What about the direction of the solution, the unit vector? Well, it's gonna still spins forever, isn't it? Because we are in an ellipse. It does infinity many turns. And then known. And characterize this solution. What is this solution? Well, there are names for these graphs, and the name corresponding to this graph when we have a spiral going outside is a spiral, is a source spiral. is like the solution is going from the center to outside, and that's it. Once you have the solution on paper, and then it's very easy to answer all the questions. You need to get all the questions correct, answer correct. So the graph should match the graph you have, and then with the graph you have on paper, and with the graph you answer all these little questions, and hopefully everything is correct. So you need only one attempt to do these problems, and the important thing is to have the correct graph. Okay, we are back to with our notes, and now we can summarize everything we have said. We answered already this little problem on the webboard site, actually. Now, as a summary, phase portraits, complex eigenvalues. So recall we are in the case where lambda has this form, alpha plus minus I beta, and the eigenvectors, the corresponding eigenvectors, have the v plus has this real part and this imaginary part. And then we have three possibilities, we said, for the graph. The first possibility is alpha bigger than 0. We call this type of graph a source spiral because the solution is coming from the center to outside. In the direction of is called unstable. We are gonna see that in a minute why. Then we have the other case, which is alpha negative, and the solution here goes towards the origin, so it's called the sink spiral. Again, the direction of rotation in these two cases and in all cases is from A to negative B. Let's put here negative B to emphasize that because it's kind of important, negative B. When alpha is 0, well, we don't have an spiral anymore. We have an ellipse, and we always move on the ellipse to in a finite distance to the origin, and we never go to infinity. And we call that case a center. And the direction of rotation is always from A to negative B, or if you are working with the second fundamental solution, it's going to be from B to A, but these two directions are the same direction of rotation, so you just have to remember A to negative B. And recall we said in this case this is clockwise, but as we saw in the interactive graph, if the vector B is in the different position, for example here is B, then the rotation is going to be in the opposite direction because of the relative positions of vectors A and vector B. So what is this last name here, stable, unstable? Well, that is related with the behavior of other solutions. So suppose we are we give in our system initial data 0. Well, we are not going to move. We are going to be right there at 0. But what happens if we give to our system initial data a little bit different from 0, but super close to 0? Let's say here. Well, we are going to start spiraling away. And no matter how close is the initial data for your system, the behavior of the solution is going to be the same. It's going to spiral away from 0. This is the opposite to happens here. If you are at 0, you stay at 0, but if you give initial data close to 0, you go back to 0. And if you give initial data super far away, it doesn't matter. At some point, you're gonna go back to 0. So the behavior of the solutions of the other solutions with other initial data, close to 0 or different from 0, is very different in this picture or in this picture. When alpha is positive, all solutions except the solutions with initial data identically 0, all other solutions go to infinity. And here all the solutions go towards the origin. This is similar to what happens when you have, for example, a table and you have a pencil and you want to stand the pencil on the tip. If you put it perfectly vertical is going to stay. That would be the solution 0. But that is not possible in nature, so there's always going to be a little bit on one side of the other, so initial data a little close to 0 but not equal 0, and the pencil is going to fall one way or the other way. So the solution is going to go to infinity. The pencil standing on a tip is an unstable situation, and that's why this system with alpha positive is called unstable, because it resembles the pencil standing on the tip. This solution here with alpha negative resembles a pendulum hanging. You move it one little bit outside equilibrium, the pendulum tries to go back to equilibrium. So you start outside 0, and the solution tries to get you back to 0. This is what happens. When that happens, we say, well, the solution is stable because the pendulum tries to go back to equilibrium, so that physical situation is called stable. So we use stable also for this type of pictures. And center is neither stable nor unstable because it stays at finite distance from the origin and doesn't go to infinity, so it's something in between. And this is the general behavior of solution with complex, the solution of 2x2 linear system of differential equations with complex eigenvalues. Okay, now let's move on to our last case. Recall we studied the case of solutions of our 2x2 system with complex eigenvalues for the characteristic matrix, and now today we are going to move to this case, the case where the coefficient matrix here in the system has real eigenvalues and different. In this case, the fundamental solutions are exponential times the eigenvector and exponential t times the other eigenvector. These are the two fundamental solutions, and the general solution is an arbitrary linear combination of these two. So what we are going to do now is see what is the phase portrait of solutions of this solution, then of that solutions, and then we are going to see that we need more solutions. In the case of complex eigenvalues, the fundamental solution, if you graph one or the other, is enough to understand what is going to be the behavior of all solutions. They are going to be spirals. They are going to be a combination of two spirals. That is another spiral. But here, the situation is different. We are going to see that this solution is a straight line in the phase space. This is another straight line, but the combinations are not straight lines. So we are going to need to study many more solutions to get an idea of how the phase portrait looks like in this case, in the case that we have eigenvalues real and different. Alright, let's go to study that case. So here we are, real eigenvalues. So here we have the solution we want to graph is a linear combination of the first fundamental solution and the second fundamental solutions, and the combination constants are called C plus and C minus. So we want to graph several solutions for several choices of C plus and C minus. And we also have different cases for the eigenvalues and also for the eigenvectors. Eigenvectors, we are going to fix two directions and we're going to do the graphs, and then we're going to see with an interactive graph how the graph changes, changing the vectors. But the qualitative behavior of the solution is going to be very different according to what are the signs of the eigenvalues. If both are positive, we are going to have a type of picture. If both are negative, another type. If one is positive, the other is negative, another type. So let's start with case 1. So we are going to start with both eigenvalues positive, and to draw the solution, what we need to do is something similar. Ground color solution. Something similar we did in the complex case. Draw the eigenvectors. In that case, where A and B, the real and imaginary parts, here we need the vectors are real, so we need to draw V plus and V minus, and then also draw the negative V plus and the negative V minus. Very similar to what we did before. So that should be, if I remember correctly, that should be done here. So we have, I'm choosing two arbitrary directions to draw the picture, and then with the interactive graph we are going to move them around and see what happens. So recall we are in the case lambda plus positive and lambda minus positive, and we are assuming lambda plus, that is the meaning of the plus, is larger than lambda minus, but both are positive. So let's start with a simple case. Let's start drawing the fundamental solution. So our next step is going to be draw the fundamental solutions. And let's see fundamental solutions. And we're going to draw the fundamental solution exponential lambda plus t v plus. Notice that this function is a constant vector, this vector, time a scaling factor. This is just a factor. So the solution is, the fundamental solution is going to be always proportional to this vector. It's going to be either this vector, or this vector, or this vector, or this vector. So the solution is going to be a line along this vector. And recall that this factor is never negative, so it's going to be half a line. So it's going to be something like this. Oops, I moved it. Let's do it here. It's going to be something like this. Direction of increase in time, that direction. At t equals 0, we are going to be right here. T equals 0. This is going to be t bigger than 0, and down here, if the solution is over here, for example, this is going to be t negative. So this is the first fundamental solution. Let's call it x plus. X plus of t. That's it. It's a straight line. Super simple. What about the other fundamental solution? The solution exponential lambda minus t v minus. Well, recall that we are assuming that lambda minus is also positive, smaller than this value, but still positive. So the general behavior of the solution of this solution is going to be the same as a half line in the direction of v minus. So if we go here, let me see if I can write it. So the solution is going to be something like this. A straight line in the direction of v minus. So here we are going to have the direction of increase in time. This is going to be t positive because alpha is positive, lambda minus is positive. Here we are going to be at t equals 0, and down here is t negative. Some point here is t negative. So it's another straight line. And on the same way, we can do the pictures for. So you see, with these two solutions, we get each solution a straight line. But what happens if we do a different solution? Suppose we do a solution x that is, for example, let's choose here this coefficient to be 1 and this coefficient to be 1. Let's suppose we study that case. Well, so let's put it here. Let's study the case when C plus is 1, C minus is 1. Then what we are going to have is, too close, there. What we are going to have is exponential lambda plus t v plus exponential lambda minus t v minus. And this is not going to be a straight line anymore, this solution on the phase space. Because how we can see that? Let's plot this solution at t equals 0. So what is this solution at 0? Well, the two exponentials are going to be 1. And we are going to have v plus plus v minus. So here v plus is the addition is more or less over there. Okay, so let's do it more or less, I don't know, over there. So this is going to be the endpoint of the solution vector. This is the solution vector, and this is t equals 0 now. Okay. Now, what happens in the limit that is t equals 0? What happens in the limit t much bigger than 0? Well, because lambda plus is bigger than lambda minus, then that is gonna say that exponential lambda plus t is much bigger than the exponential lambda minus t. The same t, the lambdas are different, the exponentials are different, but both are going to be much bigger than 1. So what is going to happen is we are going to move in that direction, but we are going to, if we move along the direction of the fundamental solution in exactly the same way, this point should go along this line, should go away along this line as t goes to infinity, but not. The factor in front of the solution b plus is much larger than the factor in front of b minus. So while here we are going to move, let's say, a little bit, here we are going to move a lot. So this point, instead of staying in this line, is going to move in that direction, in the direction parallel to the solution with a larger eigenvalue. So essentially, we are going to move maybe something like this as t grows. That's a horrible arrow. Let's do a better arrow. And we are moving in that direction. And this is t positive. What happens when t is much less than 0? Well, now we are going to have a negative number here and a big number there, a negative number and a smaller number here. So what is going to happen now is that although they are going to be bigger than 0, the exponential lambda plus t now is going to be much less than the exponential lambda minus t, which is going to be much less than 1. So what that says is when t is negative, we are going towards 0 on both directions. So in this direction we are going towards 0 because t is negative, but because this number is larger, along this line we are going to 0 faster. So the solution is going to have almost nothing in this component or almost everything on this other component. So the solution at the end is going to try to get parallel to, okay, let's move this thing away from the line. So what is going to happen is the solution is going to try to be parallel to that solution with a smaller eigenvalue, and it's going to be the direction of increasing time doesn't change. We were taking the limit t goes to negative infinity, but this here is going to be t negative. And you see the solution, the addition of the two solutions now is not a straight line anymore. It's a curve that is tangent here, then goes to the t equals 0, the addition of the two vectors, and then goes to infinity parallel to the other vector. So the solution here goes, try to be parallel to this vector at infinity, and at negative infinity tries to be parallel to that vector. We are going to see that in an interactive graph in a simpler way. We have a graph, three solutions. This fundamental solution, and the addition of the two fundamental solutions. 3. We can always do more solutions. For example, we did that solution. Let's do the negatives. if we do the negatives, well, the negative of the first fundamental solution is going to be this solution here, going away from the origin. This is solution number 4. Solution number 5 could be this solution, again going away from the origin. Nope. Complicated. There. So now we have one solution, 2, 3, 4. All the solutions going away from the origin. If we repeat the same analysis we did here, but with, for example, 1 and negative 1, or with negative 1, negative 1, or with other combinations, we are going to have more solutions that they are going to look essentially like this. Going away from the origin. Here, going away from the origin. And we are getting like a fork, a double fork. Everything going away from the origin. So we get a fork, and in this case, the fork is along the eigenvector with the larger eigenvalue. So along this direction is where everything is bending towards when t goes to positive infinity. So here we have 1, 2, 3, 4, 5, 6, 7, 8 solutions. And now we have a picture of what is happening with all solutions. So in this case, case 1, alpha lambda plus bigger than lambda minus. If you repeat this, so what do we do to find this picture? We draw the eigenvectors, the negatives of the eigenvectors. Then we draw the fundamental solutions. And then we study only one solution, linear combination, and we study the case t equals 0, t very large, and t very negative, large and negative. And we study the exponential, the behavior of the exponential, and we get these curves. So that is the case, both eigenvalue positive. So now let's do the other case, just to have an idea, a little bit more practice. This case, both eigenvalues negative. And how do we do it? In the same way as before, solution. We start drawing the vectors. So the first thing to do is draw the vectors v plus, v minus, minus v plus, minus v minus. Hopefully it's here. Let's suppose we have these vectors as the v plus and the v minus. Now notice both eigenvalues are negative. So this is the direction of the eigenvalue. This one is the direction of the eigenvalue lambda plus, which is negative, is less negative than lambda minus. This is more negative. Here. So now we draw the fundamental solutions. The fundamental solutions. So now we draw the solution exponential lambda plus t v plus or minus, and then this exponential lambda minus t v minus, again plus or minus. So these are 4 solutions. Here is one solution. Here is the other solution. Let me see. Oh, okay, right there. I don't like the arrow because I don't want arrows right now. There. Then we have the other solution here and another solution right here. But what is the direction of increasing time? Recall, all these numbers are negative, so when t increases, these factors shrink. They become smaller and smaller, so the direction of increasing time actually is towards the origin now. in all these solutions. And here we have towards the origin. Doesn't matter where you are, you go towards the origin now. Let's make it a little bit bigger and a bit better. So you're going towards the origin, no matter where you start, because all the eigenvalues are negative. And also here. And here. So this is the direction of increase in time. Okay. At t equals 0, we are at the eigenvalue, at the eigenvector. So this is t equals 0. In all this, t equals 0. Okay. T positive, we are shorter than the eigenvector, so this is t positive. And then this has to be t negative. And this arrow is horrible. Okay. And the same here. This is t0, this is t positive, and now this here is t negative. So we are going towards the origin with all 4 solutions. And now the only thing we need to do is draw one of the solutions. For example, consider the case c plus equal 1, c minus equal 1, like we did before. And let's plot this solution, which is going to be exponential lambda plus t, v plus exponential lambda minus t, v minus. And we plot it at t equals 0. The solution at 0 is going to be v plus v minus, like we did before. So we are going to be more or less in the same place we were before, more or less here. All right. Now what happens, now this is the different part, what happens when t is much larger than 0? Well, we have the exponential lambda plus t and the exponential lambda minus t. Recall, these are negative numbers now. T is positive, is super large. This number is more negative than that, so this number is gonna go to 0. Both go to 0, but they are gonna go to this number is gonna go to 0 much faster than this number. So we are gonna have that. This is positive always, and this is less than 1, much less than 1. So when t is negative, when t is positive, what is happening is we are going towards the origin, like we saw before. So this point is going towards the origin, but the contribution of this factor is going to disappear faster. So it's going to be parallel to v plus, the solution. So the solution is going to be parallel to v plus, like this. And we are going towards the origin. And what happens when I'm running out of space? So let's create more space. What happens when t is much less than 0? Well, we have negative number. So let's copy these two things here. Copy here. So we have negative times negative. This is a positive number. Negative, this is a positive number. And now this number, because lambda is in absolute value is bigger than lambda plus, because it's more negative, this number is way bigger than the other number, and they are both much bigger than 1. So what that says is this part of the solution is much more important than this part. The solution becomes parallel to v minus. So we are moving like this. Again, going towards the origin for t increasing. But here is t negative, here is t equals 0, and here is t positive. So this is one solution. If we do the other solutions, we are going to complete the fork. That was not good. We are going to complete the fork more or less like this. That is not good. again towards the origin. We are going to complete the fork like this, again towards the origin, and we are going to complete the fork like this. Like this. So what we end up with is with some sort of fork, but the fork is along the direction of the more negative. Before we have a fork in the direction of the more positive when the both eigenvalues were positive, and now it's a fork in the direction of the more negative eigenvector. And if you study the case one eigenvalue positive and the other negative, you're going to end up that the picture is more or less like this. So we can put all these pictures together in one little place like this. Both eigenvalues real and different. Well, the picture depends on the relative signs of the eigenvalues. Both positive, we have a fork along the more positive. Both negative, we have a fork along the direction of the more negative. When one is positive and the other negative, we have this kind of saddle or behavior that you go in this direction, the direction of positive, you go away from the origin. In the direction of the negative, you go towards the origin. And when you are in between, you approach the origin and then you go away. You approach the origin and you go away. Approach the origin and goes away. Approach and then go away. The only way you can reach the origin if you are in one of these fundamental solutions. This goes to the 0. Otherwise, you get closer and you go away. So this is you can see the names sync node here for the solution 0 because everything goes towards the origin. Source node because everything goes away from the origin. Node is just to emphasize is not a spiral. So that's why node. And saddle, well, sometimes you get closer and you go away, or you go away and only along one particular direction you touch the 0. Otherwise, you always go away. We call that saddle, and we call them stable, unstable, and unstable. Same analogy with the pencil standing on the tip. If you get a solution close to 0, here you go away. Solution close to 0, you go away. Here, any solution, you go towards the origin. And here, most of the solution goes away, except solutions along this line that goes towards the origin. So it's essentially unstable. We call this two unstable, and stable, that solution. So now let's see these solutions in an interactive graph. Okay, here we are in the interactive graph that you can find in our class page in interactive graph GeoGebra, and now you need to find this interactive graph, real different eigenvalues. As before, we have the eigenvectors v1 that is v plus and v2 is v minus. The smaller eigenvalue is here, the larger is there. And unlike in the previous case here, in the paper here, you can move them on different positions, but we keep it like that. So here you have lambda plus, which is positive, lambda minus is negative. Okay, so let's put both positive first. Let's put this to be, for example, 1, and let's move lambda minus also to be positive. So, for example, a little bit smaller, maybe 0.5. Okay, something like that. So there we have lambda plus 1, lambda minus 0.5. So this is bigger than that, but both positive. So what solution do we choose? Let's choose fundamental solution, so both coefficients equal 0. These are the coefficients in the linear combination of the fundamental solutions. Let's plot that, and at time t equals 0, we are... Oh, I put 0. That is not good. So if I put 0 in both coefficients, then I only get the solution 0. So that's why the dot. So actually, I want a fundamental solution. The fundamental solution be lambda plus. So this coefficient 1, the other 0. Okay, now we are going to have the line. And notice that when time increases, we get, it's hard to see, but the solution you see is going away from the origin. Alright, it's along that line. what happens when we put the other fundamental solutions and we kill this one? Well, we are going to have the other line, again going away from the origin as when we move time. Okay, and what about the other fundamental solutions? Well, the other fundamental solution is this is equal 0, the other is -1, there it is, and then this is 0, and the other one is -1, and there it is, the other solution. Cool. Now what happens when we have both fundamental solutions? This is the one we graph the plus, the fundamental solution plus the fundamental solution minus. Well, this is the curve, remember, that we got. So when t goes to infinity, we go away, but the component along the solution with the larger eigenvalue is more important than along the smaller. Both go to infinity, but you see what happens with the unit vector. It has a limit now. The solution goes to infinity. It's hard to see because it's so far away, but the unit vector has a limit. The limit is the eigenvector v plus, the direction of v plus. And when we go to at 0, we are there, and then when we go to negative infinity, we don't see the vector because it's so close to 0, but the unit vector gets parallel to the vector v plus. So in this case, the solution unit vector has limit, either one eigenvector or the other, for this fundamental solution. But we have many others. We have, this is the fundamental solution, and then we have the other solution, this one here, that we didn't plot, but here is the fundamental solution, that one. Then here we have another one, and then this one here, -1. So these are the 4 solutions we had in the graph before, and now we can draw only one at a time. In the picture we did it all 8 together. What happens if we move the eigenvectors? Well, the solution changed the form, but the general behavior is the same. General behavior doesn't change, so only the details. Okay, so let's put the vectors where they were, here, and maybe here perpendicular is the best picture. And what happens when one eigenvalue is negative, like here? Well, this is the picture we saw. You see that it approaches and then goes away, and then this one here, the same, from negative infinity towards the origin and then goes away. And that one here, this is a different solution, again from negative infinity, so from the direction of the eigenvalue with negative eigenvector to the direction of the eigenvector with positive eigenvalue. This is the negative, this is the positive, plus and minus. And when both eigenvalues are negative, so let's make this more negative, and then let's make this one negative, then the solution goes towards the origin. And the fork is going to be along the direction of the most negative, which is this one. And here are the 4 solutions. So this is how the fundamental solutions and other solutions behave in the case of real different eigenvalues. And here you have all possibilities. You can put some signs for your eigenvalues, both positive, both negative, or one positive, one negative, and you have you can move the vectors here if you want, and you have you can get intuition how the solution behave. Once you know how the solution behave, again in the homework you can answer all the questions about the behavior of the solution. Here you have the solution vector and the unit vector. So use these pictures to get intuition to solve the homework problems. So that's all for this video. Hope to see you in the next video.